Now we want to establish the same result, but now f of xy being the same function we used previously, and c being a closed curve. And I should have noted last time, I'll note this time, this is integrated counterclockwise, where C is any decently behaved curve enclosing region R, which contains the origin. Now, previously, we did this for any circle around the origin. Now, we're doing it for any curve enclosing the origin. So I need to draw a picture. If this is the xy coordinate plane with the origin here, then C will be any decently behaved curve enclosing a region R which contains the origin. That means, very simply, that the curve bounds some region R, and the origin is within R. There's our origin within the region. Now, this would be true for any curve, which I'll call C1, wording's getting a little clumsy here, but we'll say consisting of a circle centered at the origin. That was just proven in the immediately preceding video. So let's take our curve, let's draw a little bigger picture. Doesn't look exactly like it did before, but let's say now here's the origin. And let's draw a circle C1 about the origin. And let C1 be a circle about the origin, lying entirely within our region R. Since the origin lies in the region R, there's got to be a little room around the origin, enough room to draw at least a tiny circle centered at the origin. So under the stated conditions, it's possible to do this. Now, we're going to construct a closed curve, a closed path, that includes both C1 and C, the boundary of our region R. And let's go ahead and label C being the boundary of the region. So the curve is going to go like this. And we're going to start, well, we can start any place. Let's start right here. And then let's move around the curve C in the positive direction. So we're going to start moving in the positive direction. We're going to trace our way. If I can stay on the line, we're going to trace our way around this curve. Now, we get around to here, and what we're going to do is we're going to jump over to the curve C1. So we've come around to here, Now we're going to jump down to C1, and we're going to go around C1 in the negative direction. So we're going to go around C1 this way. And then we're going to come around. We get around to this side, and we're going to continue. I'm going to draw the other path in blue in just the opposite direction, right along the same path that we used before. And there's nothing, well, actually, yeah, this curve has to be closed, and it has to be non-intersecting, so we draw this very, very close to the curve we had before. And then we simply continue back around the rest of our original curve. So that our path consists of a path all the way around C and a path all the way around C1 in the opposite direction. Now, I should really say almost all the way around C, because we do have a little gap here where we split off and then came back to not quite the same place, but very, very close. And a little gap around C1 where we split off and did the same thing. Now let's enlarge this little part of our path. We have our part of our curve C coming along here, and we have our curve C1 down here. And I've only drawn part of each of those curves. Well, actually, let's go ahead and draw all of C1. It's going to be a really bad looking circle, but let's pretend. Origin here. Now, when we split off of C and came down here and then came around the circle, we came back to a point that wasn't quite exactly where this curve hit. There's a little bit of space between these curves. So what we actually did was we left out just a little bit of C1 and we left out just a little bit of C when we did this. Of course, having come back here, we continued on along C. We did that because our entire curve here can't intersect itself. So that these two segments are very, very close together. Okay, this segment and this segment. Very, very close together. The values of F are very close. At what I'm going to call corresponding points, and for at least some degree of brevity here, I'm not going to go into too much detail, but what I mean by that, I just mean as we move along this curve, we just let's say these two segments are parallel, so that we simply move at right angles from one point of this curve to a corresponding point of this curve. Then, since these curves, the space between these is practically zero, very, very close to zero, there's no room for F to vary by much if it's a continuous and differentiable function. So that the integral over the red curve going this way and the integral over the blue curve going this way are very nearly equal and opposite.